This is Brennan Lundquist, and for my 425 project, I built an electric longboard. The longboard was made using birch plywood and fiberglass sheeting. The sheeting was sandwiched between layers of plywood and held in place with epoxy. The longboard was then placed into a mold, which allowed it to retain its shape and form together as a single blank. And then the longboard was cut out from that blank. From there, the trucks and wheels were attached, and the longboard itself was complete. Unfortunately, due to an error in the machining process, the actual electronic system cannot be attached to the longboard. To fix this, I'll need to purchase new gears or remachine the current gear so that I can actually mount it. Instead, what I did was just build the full electronic setup and then test it on a bench to tune it in to get it working. The electronic setup used a brushless motor, a speed controller, battery, the TIVA board, and a potentiometer for analog input. The way the circuit works is that the TIVA board reads the voltage across the potentiometer and uses that to deliver a PWM signal to the speed controller. The speed controller then takes this signal and draws current from the battery to power the motor to a desired speed. I made custom batteries to use with this device, but the batteries ended up having bad cells and did not work, so instead I used an existing battery that I had. The battery had a lower voltage than my original batteries, which meant that the circuit itself would be less efficient and would draw more current and reduce the battery life, but this was considered acceptable for the test setup. The potentiometer used was salvaged from a gamepad. It has a small potentiometer in it that's connected to an analog stick, so when the analog stick is adjusted, the potentiometer position changes, allowing a different voltage to be read off the potentiometer. The code was written in the Energia IDE and downloaded the TIVA board. The code configured one of the analog pins to accept the input from the potentiometer and mapped this value to a specific output as it correlated to a PWM value that was needed for the ESC. The potentiometer voltage was recorded and assigned a value from 0 to 4000. I tested this using the serial monitor in the IDE. The values were then mapped to a scale of 0 to 180. The scale of 0 to 180 was needed in order to send the correct pulse signals to the ESC. The first code proved not to be sufficient because the response was not damped nearly enough. The motor changed its speed very quickly and go from full stop to full speed in under a second. This would not work properly with a longboard because the user needs to be able to slow down and speed up at a safer speed. So instead, code 2 was developed. This code simulates a curve to change the value that's written to the speed controller. Instead of directly writing the input values, the response is damped by allowing it to slowly change to the desired value based off the delay time. So if the delay time is shortened, the response will be faster, and if the delay time is lengthened, the response will be slower. This allows it to be more easily tuned to user comfort. The damp system proved to be much more effective for this purpose and allows a lot more user comfort and also tunability. For future systems, I want to increase the complexity of the feedback curve so that there is more room to tune the responses at different speeds. Another change that I want to make at some point is to include a Bluetooth unit so that the potentiometer can be moved to a handheld remote and the signal can be transmitted down to the board. That way that there's no physical connected wire connecting the controller to the board. This would require a voltage regulator circuit for the Bluetooth transmitter. I also want to finish the mechanical assembly by buying a new gear, machining a mount for the motor, and putting everything in a protective case underneath. While I was not able to get the actual board itself working, I was able to complete the electronics for this project, and it really showed that it's not overly complicated to send pulse signals through the TIVA board, and it really opens the door for a lot of robotics control and other servo type controls that can be accomplished with the TIVA. I really enjoyed this project, and thank you.